Okay, so we've seen the example through which the connection was made, and what's left to discuss is the general case. So what I want to do here is give you two theorems, one the generalization of the first, and then discuss it in a couple of examples. Okay, and I'm giving you these theorems without any proof. So the first is about deterministic measurement-based quantum computation. Did we have a theorem yet? Yeah, we had the Cauchy-Specker theorem. So let's make this theorem too. So it is about the computation of a nonlinear Boolean function, and we want this computation to be deterministic. Okay, so this is what we are talking about. And now what do we say? We say that this measurement-based quantum computation is contextual, i.e. it cannot be described by a non-contextual hidden variable model. Okay, so this is the first result. Before we go to the examples, so there's one word in this theorem that you might take issue with, and that's deterministic. Yeah, that is certainly a very special case. And yeah, can we remove it? And the answer is yes, we can. We have a more stringent theorem that requires less. It doesn't require deterministic quantum computation. It only requires the computation with a certain success probability, and that success probability have to be above a certain bound. And the theorem says precisely what the bound is. And so let me write down this slightly more general theorem that talks about probabilistic measurement-based quantum computation. And once we've done that, we will be looking at two examples. Okay, so that's what we're talking about. An MBQC computing a Boolean function with a probability PS. And now we success probability, that is. And so now we need to specify what that is. So it has to be above a certain value. It has to be bigger than 1 minus okay. Good, so that is the condition. And then what we are saying is contextual. Okay, so this is the new theorem. Okay, so let's try to pause this. So what's coming up here? So we have m we introduced before. So m is just the number of input bits in our function, in our Boolean function that we are computing. And what is this object over here? So this is the Hamming distance from the function f to the closest linear Boolean function. Okay? And success probability is given by this expression. If it is larger than this, then our measurement-based quantum computation is still contextual. So to kind of try to absorb what this means, let's look at two examples. Or just as I'm writing this, let's check a linear Boolean function. This just came across it. I didn't mean to talk about it, but it's an interesting limiting case. So when you have a linear Boolean function, so that distance to the closest linear function is 0. So well, for a measurement-based quantum computation, computing a linear function to be contextual has to have a success probability that's larger than 1, which of course doesn't happen. So whenever you compute a linear Boolean function, there's never going to be contextuality. Okay, so that's just as a consistency test. Now let's talk about the two examples. So, example number 1 is the OR gate. So that case was m equals 2, which we will need here. Yeah, so we need to figure out, so now our function is the OR gate, computed on 2 bits, and we need to figure out the distance to the closest linear function. So if you, for example, take as your linear function input bit A plus input bit B modulo 2, that is a distance 1 away from the OR gate. So the Hamming distance must be 1 or smaller, but it cannot be 0 because if it were, then the OR would be a linear function. So the Hamming distance from the OR gate to the closest linear function is indeed 1. Okay, so we are using this in our expression here. So m is 2, so we have 1 over 4, and so the MBQC computing an OR gate is contextual if the success probability computing it is above 75%. And I guess you have heard that number of 3/4 before. So this is our first example. Okay. Example number 2. This is now for m even. And the question that we are now asking is, how low can this threshold be? And this invokes a particular type of function. So we are assuming, without knowing how to compute this, but we are assuming that our measurement-based quantum computation is able to evaluate so-called bent functions. Bent functions are the most nonlinear in the sense, I should say, bent is a proper term in coding theory. It's the coding theory context in which these functions came up. And so the bent functions are the most nonlinear functions in the sense that they have the largest distance from the set of linear functions. And from looking at this expression here, you see that that is precisely what we need to make our success probability bound as low as possible. Okay, so what do we have for the bent functions? It is 2 to the m minus 1 minus 2 to the m half minus 1. So this is a known result from a coding theory textbook. Yeah, you can find it. So what does this imply on our bound for the success probability? We just take this Hamming distance and plug it in here. So we find from the first term 1/2, and that's important. Now, from the second term, so it's 1 minus, we have a minus, so it becomes a plus. Okay, so this is the expression. So what's interesting about this expression is that the first part is complete randomness, and the second part is just an epsilon. So even if you're just the tiniest bit above complete randomness, you're still contextual. Okay, so that's why I wanted to show you this example. Okay, so this is basically it. So I have only one more thing to say, and I only have a tiny bit of space left. So let me summarize. In measurement-based quantum computation, nonlinearity implies contextuality. Okay, nonlinearity implies contextuality, and that's the summarizing statement for this lecture.